Hello again, this is a second video in step 4.1 of Fundamentals of Physical Geography, and we're talking about the energy sources that affect physical geography at the Earth's surface. So the features and distributions of phenomena at the surface are controlled by processes that are driven by energy. This energy is derived from the Sun and from the Earth's interior and from gravity. But particularly from the solar energy, also from Earth's interior energy, the supply of energy to the Earth's surface is uneven. And it's this uneven distribution of energy which is key in determining the distribution of processes and mechanisms, the geography, if you like, of physical geography around the planet's surface. As it says there, the uneven energy supply explains many features of Earth's geography. The atmospheric and ocean circulation serve to redistribute solar energy around the globe. Geothermal energy drives plate tectonics and volcanic processes. Gravity is a key driving force in geomorphology. So gravity, solar energy, Earth's interior energy, between them are driving lots of the big things that we think about as being central to what physical geography is all about. The supply and redistribution of energy is at the heart of physical geography, and that's what we're talking about in this session. Let's talk about solar energy first of all. Some facts and figures for you here. We explained about the watts per meter squared notation in the previous video. So at the sun's surface, it's issuing 63 million watts per meter squared. That's the brightness, if you like, or the energy at the Earth's surface. And remember, we talked previously about the relative sizes of Sun and the Earth, and the distance away that the Sun is from the Earth. It's 94 million miles away, and if the Earth were a 1 centimeter marble, the Sun would be 120 meters away, and it would be a meter across. So the Sun's a long way away. The energy travels a long distance, spreading out from its central origin, and by the time a portion of that energy reaches the Earth, this is a key figure for you at the bottom of the screen there. The solar energy arriving at the outer edge of Earth's atmosphere, about 1.3 kilowatts, 1,360 watts per meter squared of that outer atmospheric surface. That's how much energy is arriving from the Sun onto the Earth. Now, one of the first things that you need to read up on and become confident about is the radiation balance, the Earth's radiation balance. Rather than worrying about the exact amounts, we've just called the incoming solar radiation that we referred to in that previous slide 100% incoming solar radiation. Of that, only about 50% reaches the Earth's surface, and of that 100% incoming radiation, because there is a balance in the radiation budget, if you like, the incoming amount matches the outgoing radiation. Now, you need to read up on the details of exactly how that balance is maintained, and you need to be aware of the fact that, of course, if we have more solar energy coming in and it isn't all escaping, or it isn't all going out again as outgoing radiation, then we don't have a radiation balance, we'd have a radiation imbalance, and that could be problematic, obviously, for our future on the planet. So of the incoming solar radiation, about 30% is reflected and backscattered by the Earth's surface or by air, clouds, and so on. And that goes back out as shortwave radiation. About 20% is absorbed by water vapor, clouds, dust, ozone, and other things. And that, again, is re-radiated. And about 50% gets down to the surface. Of that 50% that's absorbed by the surface, about 20% is radiated directly away again, some of which goes straight out as long wave radiation and some of which is reabsorbed by the atmosphere and then re-radiated, and about 30% is transferred back to the atmosphere as sensible or latent heat. Now, I'm not going to talk about this in detail because this is a topic that you can read up on. There are some very convenient diagrams in your basic textbook and other sources. But I just want to encourage you to get to grips with the basics of incoming radiation, what happens to that in terms of local absorption, re-radiation or reflection, and this concept of there being a balance of energy in and energy out. Now, I'm sure this is a really interesting topic, but rather than getting bogged down in the numbers, what I'm going to focus on is the geography of this pattern, which it doesn't really feature on this diagram. And the key point for this session is that insolation, that incoming solar radiation, it isn't distributed evenly around the planet. The first reason for that uneven distribution of energy is the Earth's round shape. The Earth doesn't present a flat vertical surface to the incoming solar radiation, as on this diagram. In the summer solstice here, where the northern polar area is pointing towards the sun's rays are vertical overhead. The sun appears to be overhead at the Tropic of Cancer, but then at higher or lower latitudes, the sun's rays aren't coming in that concentrated vertical pattern, but they're coming in more obliquely, so this solar radiation is spread over a greater area of the Earth's surface. So thinking in terms of the watts per square meter, these watts are being spread over a greater number of square meters or square kilometers than at this location. And this diagram illustrates the amount of radiation being received at the top of the atmosphere. We'll think about what happens to the radiation as it makes its way through the atmosphere in a second. But this is the amount of energy received at the top of the atmosphere through the year, January, February, March, April, May, etc. And by latitude, South Pole, Antarctic, Capricorn, Equator, Cancer, Arctic Circle, North Pole. So northern and southern and equator, and here through the year from January through to December. And this picture is a result of what we saw in the previous slide about the shape of the Earth and the sun's rays coming in at a more or less oblique angle, combined with what we talked about in a previous session about the tilt of the Earth's axis and the orbit of the Earth around the sun. So, for example, in January, the southern hemisphere is getting a lot of solar radiation. The Antarctic is pointing towards the sun, 24 hours daylight, whereas the Arctic is pointing away from the sun and is getting no daylight at all. But as we work our way through the year, that shifts around. So the Arctic gets no daylight, no insolation during the winter, lots of insolation during the summer, and then none again as we head into the following winter. The opposite is true in the Antarctic Circle, or rather the timings of the winter are different. In Antarctica, January is the Antarctic summer, lots of insolation. The southern hemisphere winter in May, June, July, August, the South Pole is getting no insolation whatsoever, and then by the time we come through to the following Antarctic summer, they're getting the sunshine, whereas up in the northern hemisphere, the high latitudes aren't getting the sunshine. So there's a great deal of variability through the year at those latitudes. Around about the equator and the tropical regions, there's less variability through the year. So there's less variability here, but on balance, we're getting more radiation here and less at the poles. And that geographical variability is illustrated on this map that also gives you some numbers to put to that. So the previous slide showed the variability through the year very well. This one illustrates the geographical variability very, very well. And again, we're talking watts per meter squared energy arriving at the top of the atmosphere from the sun. And you'll see in the tropical regions around the equator, between the tropics, there's a very high level of incoming solar radiation. And as we move away from the equator towards the poles in both latitudes, there's a diminishing amount of radiation coming in until the incoming solar radiation in the extreme high latitudes is very low. So there's a huge imbalance between high incoming radiation here and much lower incoming radiation there. Now, the way that solar radiation and radiation of energy away from the Earth works means that incoming sunlight, shortwave radiation, comes in with that geographical variability that we talked about, with a lot more energy coming in at equatorial latitudes and a lot less energy coming in at higher latitudes. But the loss of energy, remember that we have a balance, incoming radiation balanced by outgoing radiation. The loss of radiation isn't geographically variable in the same way. The Earth is radiating in a less geographically specific way. So if we combine all those bits of information that we've just taken in, we then come to diagrams like this that show us the net radiation, or if you like, the radiation balance in terms of whether we have more radiation coming in than going out, or more radiation going out than coming in. And around the equatorial zone, we have a positive balance, if you like. There's more radiation, more energy coming in than there is going out. So we're up on this side of the scale with positive numbers for the net value. Whereas in the polar regions, we're at the other end of the scale with negative numbers. We're losing more energy from here than we're actually putting in from solar radiation. So there's a net imbalance with positive in these areas and negative in these polar areas. And it's that imbalance in energy that drives a lot of Earth's surface processes as the energy is redistributed to try to even up those geographical disparities. Now, this isn't a realistic picture of how the atmospheric circulation works, but this is a first attempt, a very simple model, if you like, of how you'd expect the Earth's atmospheric circulation to respond to that simple picture that we've so far given you, where we have high radiation, positive radiation budgets in the equatorial zones and negative radiation budgets in the polar zone. So high energy, more warmth, low energy, cold environments at the poles. What you would expect to happen there is warm air to rise at the equator, to move away to the poles, cold air to sink, to travel over the Earth. And so we're redistributing the energy by moving energy between the high energy zones and the low energy zones, with surface flows responding to the higher level flows in the atmosphere. And in a simple situation, you might expect that single cell circulation. You can see here it's sometimes referred to as a Hadley cell. Now, in a previous session, we talked at some length about a process or a mechanism that occurs because the Earth isn't as simple as it first seems. For example, the Earth is spinning. What does the spin of the Earth, the rotation of the Earth, do to things such as fluid flows or atmospheric flows moving across the surface? Do they flow in a straight line? You remember the Coriolis effect? The Coriolis effect leads to deflection because of angular momentum and differences in the velocity of the rotation at different latitudes. So we don't have a simple flowing pattern around the Earth like this single cell circulation. That isn't the way it works. And because of the Earth's circulation, we have a much more complicated pattern. And this is a three-cell model, a much more realistic model of global atmospheric circulation that involves complications with the multiple cells occurring and the deflections of the winds and changes in the circulation patterns because of the spin of the Earth. But again, we have the equatorial low pressure zone, we have intermediate high and low pressure zones and a polar high pressure zone, as a result of which energy is redistributed and recirculated around the planet. So that's an atmospheric response to variability in the solar radiation balance at the surface. You can identify similar kinds of patterns in ocean currents. As part of your reading around this, explore energy redistribution by global circulation systems, whether it's atmospheric or oceanic, in response to this imbalance in the radiation budget. We're going to have sessions on the atmosphere and on the oceans later on in this part of the module. But for now, I just want to flag up this idea that the movements of the atmosphere, the movements of the oceans are all to do with energy redistribution, and they all stem from this uneven distribution of incoming and outgoing radiation in the radiation balance. Now, we've talked about incoming solar radiation. I should also say a word briefly about energy coming from the other direction, energy from the interior of the Earth. Now we're going to say a little bit more about Earth materials and the structure of the planet in a different session, but at this stage just be aware that energy is supplied to the Earth's surface not only by solar energy from outside, but also by energy from the interior of the Earth, because the interior sections of the planet are at very high temperatures, and those high temperatures lead to radiation of energy and convection of energy through this inner portion of the planet out to the crust that we're interested in and the Earth's surface. So at this stage in the module, just make sure that you're familiar with this terminology of the different parts of the Earth. If you're doing geology in combination with your geography, then you'll be looking at this in a lot more detail. But for now, just be aware of the approximate scale and the broad categories of what's going on in the interior of the planet, and be aware of these temperature variations that are affecting what's going on at the surface. Now again, cutting through the detail, just as we did with the solar radiation balance, I don't want to get bogged down at all at this stage in the details of what this energy is, where it comes from, or exactly how it works. I just want to make, well, 2 points really. The first point is about the amount of this energy coming through to the surface, and I want you to compare the values here with the values that we were talking about for solar energy. So this is a map showing the geothermal heat flow through to the surface in part of North America. And you can see that the scale here, well, it varies from about 25 to about 150 milliwatts per square meter. So we're not talking about watts per square meter, but thousandths of a watt per square meter. So whereas when we were talking about solar radiation, we were talking about 1 or 2 or 300 watts per square meter, in other words, a good old-fashioned light bulb or two. Here we're talking about fractions of a light bulb, thousandths of a light bulb amount of energy coming through to the surface. So the amounts of energy that you would feel coming through from the interior of the Earth are much, much lower than the amount of energy coming through from solar radiation. That's not to say this energy from the interior isn't having a huge effect. If we think about plate tectonics, volcanic activity, earthquakes and so on, we can see that there's a massive effect on the Earth's surface from this energy, but the actual watts per square meter is much lower. That's the first point I wanted to make. The second point I wanted to make, looking at the distribution of colours on this map, simply makes the point that, as was the case with solar radiation, it's the case also for energy from the inside of the Earth that it's geographically variable. It isn't the same everywhere. Here there are areas with a very high geothermal heat coming through to the surface and areas with much lower geothermal heat coming through to the surface. It isn't evenly distributed, and that uneven distribution drives processes in different ways, in just the same way as the uneven distribution of solar energy drives processes. We'll talk about these things a little bit later in the course, but certainly when we're thinking about plate tectonics, volcanic geomorphology, volcanic landscapes, the distribution of crustal plate boundaries, earthquakes, volcanoes and so on, this energy from the interior of the Earth and the geographical variability of its expression on the surface becomes really important. So at this stage, again, just to set you off on your background reading, I'm not going to say a lot about that whole plate tectonic process, volcanic processes, impacts on continental distributions or geomorphology, but I'm just going to throw this one slide into the talk here, just to remind you that as part of your background reading at this stage, finding out a little bit about how characteristics of the structure of the Earth impact on processes that are going on at the Earth's surface would be an important thing for you to be looking at. So in this section, we've just made the point that there's energy coming into the Earth's surface from solar energy and from Earth interior energy, that we can look at that in lots of detail, which I haven't really done today, but you can have a look in more detail in your reading if you want to. And that a key point about this radiation from the sun and this energy from the interior of the Earth is that it doesn't affect everywhere on the Earth's surface equally, and there's a disparity in the incoming radiation and the outgoing radiation for solar energy, for example, that drives major processes such as the atmospheric and oceanic circulation. And the energy from the interior of the Earth drives these big circulations that underpin plate tectonics and the movement of the continents. So a lot of what's going on in physical geography can be traced back to these energy sources. And I haven't really said anything yet about gravity, but that's another key driving force that makes things happen in Earth's surface processes and in geomorphology. So in your background reading, focus on those three sources of energy, but think about their impacts on the geography and on the physical geography of the Earth's surface. At this stage, you might just want to pause the video, have a look at these questions, check your notes from the sessions and from your reading to see if you know the answers to these various questions. These are some of the kinds of issues that you should be thinking about at this stage. Maybe work through those questions on the previous slide before you finish this video, but by the time you get to the end of this and by the time you've done some background reading, these are some of the key points that you should be beginning to become clear on. You should at this point be able to describe the major sources of energy that supply Earth's surface processes. You should be able to summarize Earth's radiation balance. You should be able to describe how the uneven distribution of solar energy drives energy redistribution processes such as the atmospheric circulation. And you should be able to recognize the relationship between Earth's interior heat and processes such as plate tectonics.